and welcome to Tuesday's edition of Cracking the Cryptic. Now, some of you complained yesterday that I seem to have had a day off with just a sub 20-minute video. I think you're going to get your own back today. This puzzle on the screen is called FRAK, and it's by Zetamath, and it has a 100% rating on Logic Masters Germany, but also 5 stars out of 5 for difficulty. I have read the rules. I suspect this is going to be an absolute mission. So yeah, you'll know better than me. If I've managed to solve this, obviously this will appear as a video, and you'll simply be able to look at the video length to know how badly I've struggled with it. It's got some very interesting rules, but I have to credit Zetamath tremendously for titling his puzzle in line with the old BBC Micro game from 1984, a game I remember fondly from my youth. So this was the game. It had fantastic graphics for the time, as you can see, and the FRAK exclamation mark being a 4-letter word beginning with F that was suitable for BBC Micro users. But I used to love this game. Absolutely amazing. I have no idea what this puzzle has in common with FRAK, but something, evidently. You guys will have to tell me in the comments. Now, today is the 1st of March. These are the things we reveal, these knowledge bombs on Cracking the Cryptic. And that means it is Patreon Reward Day. So if you're a patron of the channel, get over to Patreon, and there will be a new Sudoku hunt available. We've tried to make this one quite approachable as well. Like last month's, we got 1,728 entries, I think, for last month's competition. Let's see if we can beat that. Do all have a go. We hope you like what we've done this month. Let's just say there's a little theme going on. We're sure you're going to be familiar with what it is. Now, other than that, I don't think I've got anything else to tell you. I did also put a solve on Patreon yesterday of Sam Kappelman-Lyons' recent Star Battle themed on the TIE Fighter, which I thought was very, very cute from GM Puzzles. So that's another little bonus over there right now. All that said and done, I think I can delay it no longer. Let us have a look at the rules of this remarkable sounding puzzle. Here they are. Place the digits 1 to 9 once each into each row, column and region. Regions need to be deduced by the solver and consist of 9 orthogonally connected cells. Okay, so that means there's going to be 9 of them, I suppose. And we've got to build some regions. I mean, that could be a region. The whole point is they're not necessarily 3x3s in the normal way. We're going to have to make them up. And to make them up, we need to know some more things about the rules. For each blue line, digits on the line have an equal sum n within each region the line passes through. If a line passes through the same region more than once, each individual segment of such a line within that region sums to n separately. Every line must enter at least 2 regions, and a digit in a circle indicates the number of digits. The number indicates the number of digits on that particular segment of the line within that region. Not all circles are necessarily given. Good grief. Why do I have to? This is going to be impossible. Okay, I'm just trying to think if I even understand the rules. I'm not sure that I do. For each blue line, in fact, what I'm going to do, if you don't mind, is I'm just going to draw in some regions. Now, I'll be very fortunate if these turn out to be the correct regions, but let's just put some in. Let's imagine we had some 3x3 regions in the grid. Now let's read the rules again and see if we understand what this is saying. For each blue line, digits on the line have an equal sum n within each region the line passes through. So what I think that is saying is that these 4 digits here would have the same sum as these 3 digits here, which would have the same sum as those 4 digits there. Now then there's this business about if a line passes through the same region more than once. I'm not exactly sure how that can happen. Oh, okay, let's look at this L here. So let's imagine that's a region. Oh, that was a lovely choice of colour. Look at that. That actually shows up really clearly. So, no, this couldn't work, could it? Well, I mean, I'll use this as an example, but I can see why this doesn't work. I think, oh no, I could do it differently. I could do it like that. That might work. So I think what this is saying is, let's imagine this was a 9-cell region. Now you can see it actually hits this blue line in two separate ways. It's got this little cell here which hits it, and then it departs from this region and goes into another region. We don't know the shape of that region. It then re-enters, the line then re-enters the black region. Now I think what that's saying is, let's imagine this was a... No, this is impossible as well. I've still made it impossible. But the point is, I think, that if there was such an arrangement, this digit, let's say it was a 6, these two digits would have to sum to 6. What you don't do is you add all three of those up, because these, I think this is what the rules are implying. These are treated as different line segments because we've exited the region and re-entered it. Now, why do I think this doesn't work? Well, I think this doesn't work because if that was a 6, that would imply this digit also needs to be a 6, because it's and that obviously breaks the rules of Sudoku. So I've managed to mess up creating a decent example, but not on purpose, not by purpose, as my children sometimes say. Now, so what else have we got here? We've got the digits in a circle thing. What's that telling us? Let me just think about this. A digit in a circle indicates the number of digits on that particular segment of the line within that region. Right, so if this was true, we'd be saying that's a 3. Because on this line, within the green region, there are 3 cells on the segment. So this square would be a 1, 2, 3. That would be a 4, I think. 2, 3, 4, yeah. For some reason I want to put that one in, but that's not on the line, so I think it's 1, 2, 3, 4. Okay, well actually that has been helpful. I'm very sorry that's taken me a long time to work through the rules, but I just wanted to make sure that I had some sort of understanding of what was going on before I tried in earnest to solve this. Do have a go. Be under no illusion, this is probably very hard. The way to play, though, is to click the link under the video as usual. Now I get to play. Let's get cracking. I've got my window open today as well. Try and get some fresh air into the room, so there may be more bird tweeting than normal. So, what do we do here? We've got an enormous line going round the edge. I mean, how on earth do you start this? You've got... I could see... Sorry, I'm realised this is me being more inarticulate than ever, but... Okay, well I guess what we can do is we can work out the sum of all the cells on this line. I can see how to do that. So what I'm saying is that I think that we can... In fact, I think I've chosen a very apposite colour there with the yellow and the blue. That is... Well... Sorry, I realise this is worse than usual. Now, what I'm just trying to think about is, I think I can work out the value of the yellow cells. And we can do that using the secret. Now, the secret is something I only tell my favourite people. And that, of course, includes you. And the secret is that in any complete row, in any complete column, or in any complete region, but I don't have any of those yet, in any complete region of a Sudoku, you're going to have the digits 1 to 9 once each. Now if you add up the digits 1 to 9, you get 45, and 45 is the secret. And why do I think that's interesting? Well, I think that means I'm going to be able to work out the value of the yellow cells, because if this row sums to 45, and it does, and this row sums to 45, and it does, and this column sums to 45, and it does, and this column sums to 45, and it does, then the total sum of the perimeter is going to be 4 lots of 45 minus the digits in the corner, which are counted twice, because obviously this cell, or this row here, if we count that as 45 and then count this as 45, we're double counting this cell in calculating the value of the whole perimeter. So the whole perimeter has a sum of 180 minus 12, which is 168. Now that means that if the whole perimeter sums to 168, in order to get the yellow cells, I just deduct out these cells again, which is deducting another 12 from 168, which is 156. So the yellow cells sum to 156. Ta-da! What on earth does that mean? So that tells us that when we divide up the blue region into the blue line, when we divide the yellow cells into different regions, which is what we're going to have to do, we're going to have to do that such that the regions we create sum to a factor of 156. Because if we, let me use the pen tool here. By the way, if you don't know how the pen tool works, you can just click the cog icon on the right of the screen here, and you can see it says Enable Pen Tool, and this is really good for chaos construction puzzles, because basically you can draw these lines along borders. So let's imagine that we worked out that this was a region, and then this was a region, and then that was a region. Then what the blue line is telling us is that the sum of these 4 cells would be the same as the sum of these 3 cells, would be the same as the sum of those 5 cells. So altogether, if we say the sum was x, we know that we're going to have a whole string of x's. We don't know how many x's we're going to have around the perimeter, but however many x's we have, in fact, maybe that's the thing we have to do. We've got to factorize 156, haven't we? So 156 is 12 times 13. I do know that. 13 is prime. Okay, so imagine that imagine that x was 13. So this would be 13, this would be 13, this would be 13, and we keep going round. We'd have to go round and have 12 different borders in the perimeter, or 12 different. We'd have to cut the blue line 13 times, wouldn't we, to make 12 different regions. That's probably wrong, but that's what it feels like to me. So the number of regions I've got to create has to be, we have to find some sort of way of multiplying. It probably is 12 and 13. That feels very reasonable, because 13 is a very achievable total. I suppose it could be 13 regions of size 12, or 12 regions of size 13. I'm just thinking, like, what number can you get to very easily with Sudoku? And 12 and 13 feel very achievable. You know, because a 12 could be a four-digit sum, or it could be a 2-digit sum. Same with 13. Now, problem is, though, how do we prove? How do we work out what the value is around this that we're summing to around the perimeter? That's the question. So we're looking at 12 times 13. Now 12 can be factorized as well. So 12 is 2 times 2 times 3. So we're looking at 2 times 2 times 3 times 13. And we need, well, 13 is prime. So if 13... hang on a minute, let me think about this. I don't think I've ever spent as long just in silence. I'm just trying to get a handle on how this works. If you could have a multiple of 13, so I'm just wondering, could you like have regions that sum to 39, for example, and then you'd have four of those such regions, wouldn't you, in a 156? That is presumably something else I can't rule out. Ah, no, I can rule that out. Right, I can rule that out because I've got too many circles in the perimeter for it to be 4 times 39. That's right, isn't it? If I had 4 times 39, yeah, that is right. Because if I was only dividing the perimeter into 4 different regions, that would imply that 2 of these circles are in the same region. So let's imagine that these 2 are in the same region. So let's imagine that's a region here. These are in the same region, and then the yellows is not the same as the orange region. Well, that would mean I have to put the same digit into those, because that line segment within its region is of length 5, and I can't repeat a digit in a region, so that doesn't work. So that's wrong. So it's not 4 times 39. Right, okay, so let's just have a think about this. What is a reasonable number of borders along a perimeter of a Sudoku? So in normal Sudoku, I don't really want to get rid of my yellow lines, so just excuse me. In normal Sudoku, we're going to have this sort of pattern, aren't we? I can actually count this in my head, but given that I'm halfway there, so this would be a normal Sudoku, 3 by 3s, and now we're cutting each perimeter. So the north perimeter, you can see there's a border here and there's a border here, and on the eastern perimeter we've got a border here and a border here. So there are 8 cuts of the perimeter. Yeah, and it is only 8. So that 1, 2, 3, 4. Okay, yeah, okay. So I think I was wrong with my 13 and 12. So what that's telling us is that we've got here, I've got 8. I'm just wondering how many times, and I think it's 8, isn't it? Because there are obviously 8 regions touching the perimeter here, because this one never touches the perimeter, and there are 8 cuts of the border. So 8 is an achievable number. But 8 doesn't divide into 156. So we're going to have to mess around. Hang on, I'm getting very confused about how this is even possible now. How is it possible to get, to say, 12 times 13? If I'm going to cut the border 12 times, I have to improve on the geometry of this setup very considerably. And when I say improve on the geometry of it, I mean that I've got to get a region like this region to contribute more than one extra cut of the border. Because if every new region I attach to the perimeter only contributes one cut of the perimeter, I'm only going to be getting to like 8. Well, I'm only going to be getting to 8 regions. I suppose the other... Oh, hang on, I've just had another thought. Let me Control A that. But this sort of thing, if we had a total stripage of the grid like this, that's probably going to be the maximum number of times you can cut the border, isn't it? Something like this. So this is cutting the border all... Well, it's not cutting the border at all on the east and western sides, but it's cutting the border an awful lot at the top. You're going to have 16 cuts of the border here. But that 16 is not a multiple either of 156. And this doesn't work. Nothing like this works anyway, because of this line constraint. That would be implying that this total here is the same as this total, is the same as this total, and we would get into a bit of a pickle from a Sudoku perspective. So you can never have I'm not thinking about this clearly at all. I mean, this clearly is wrong, but it feels like you can never have a one cell stripe in this sort of setup at all. It just won't work. So what we've got to do instead is probably think back to our 3x3 situation. So what I think we've got to do, in order to get up to sort of say a 12 times 13 situation, it feels to me like in order to get from the base 3x3 analysis up to a cutting of the border 12 times, I've got to have regions that hit the border twice. And initially that sounds horrible, but I think it's possible. Because if this is yellow, then can't I just surround that yellow with a region like that? And that's now, so now I get the yellow contributes 2 cuts, one here and one here, and now the red is contributing 2 cuts as well, which is much better than when the red was just prompt over here, when it was only contributing 1 more cut. So now it's contributed 2 cuts. So this is the key. What we've got to do is to build up the number of ways that we can cut the border. So, but, oh no, that won't, well no, that will work. That will work. No, now I'm worried about my 1 cell strip. Because the only way that this could cut the border at a single cell. So let's imagine this region looked like this. That's a 9 cell region. But now this digit and this digit can't be bigger than 9. Well, they can't both be 9, in fact. So that gives us a problem with our 156 total, because now I have to do a single digit times another number. And we're getting into the realms of cloud cuckoo land, aren't we? What have I got to play with? I can't use 13. So 13... So that means I've got to have even more borders. If I can only have a single digit, and I'm using 2 times 2 times 3 to create the options, the highest single digit I can have is 6, which means I need to cut the border 26 times. That's not going to work. I'm starting to think I've got this the wrong way round. I think what we might have to do is to have less borders. But I can't only have 4 borders. But if I had 6 borders and each line segment summed up to well, see, yes, it's just 2 times 13, it's 26. Each line segment summed to 26, then that is probably achievable. But because the alternative to that is that we need to be able to do something like I've done on the screen here, but multiple times within the same grid. I need to create, hang on, I can give this wings, can't I? It's like Red Bull, gives you wings like that. Now I can make this add up to 13. Yes, okay. Right, so this might be it. What we could do is we could ring a 3x3 with this precise shape. That's 9 cells. And that has improved on the standard model. But now I've got to do that many more times. I can't just do this once. This is the problem here. So I could do it again down here. Let's do it again down there. So I can reach but I can't do it again. I can't do it again. It's impossible. It won't do it. This just doesn't work. I'm not sure I can give you a rigorous proof of this, like a mathematical proof, but I mean, it's just clear. Well, it's clear to me at least you can't do it with 3x3s in the corner. Because what I'm trying to do is to build a situation where I can have more than, well, I need at least 12 splits of the border, using only 9 cell regions. And although this is on the right track to doing that, because I've managed to hug this region in and it's hit the border twice, I've now got to put 5 more regions into this puzzle. But I can't create any more huggages. It's impossible. Yeah, maybe that's the way to think about it. How many more opportunities are there within this grid to create regions that hit the border twice? That's the way to think about it. And the answer is none. There is no way you can do it. Because even though I've been super efficient with my layout of the red balls and the yellows, and I've done very well with these 2 regions, you can't do it again. If I was to try and connect this cell to here with a 9 cell region, I can do it, but not in a way where this digit now is a single digit number. That's no use to me, because if I'm going for 12, I need this line segment to add up to 13 at least. And there's no other factor that we can use. So if we want to use any, there's nothing else we can use. We either need more borders, which we can't get, or we have to have less borders and a bigger total. Now, the thing I haven't done though, which is nagging away at me, so because you need 2 cells here to add up to 13 and 2 cells here to add up to 13, you can hopefully see if we try and do this, that would be how we have to use it. So that now has cut the border twice. We need a region in here that needs to be 9 cells large. That's only 7 at the moment. So we can't block anything in. So that's probably about as efficient as you can get. And now I need to connect this to this without using more than 9 cells. That just cannot work, can it? I'm saying that as an assertion, but I mean, it's nowhere, it's not even close. It's not even close. That's far too large. So, but that is all ignoring, well, that's starting with a 3x3, but 3x3 must be the most efficient way of doing this. So what I'm wondering is, can I start with a 2x4? If I start with a 2x4, surely it's harder to create a region that hugs that has wings. Where are we going to put the extra the ninth cell as well? Because we have to. 1, 2, 3, 4, 5, 6. Yeah, it doesn't work. It just immediately doesn't work, because although I can create a winged shape that surrounds a 2x4, and this winged shape is 9 cells large, the problem is I need to add another digit. I need to add another digit to the 2x4, and wherever I put it, it's going to cause the red region to be more than 9 cells. I mean, that's pretty obvious to me. Hopefully it's very clear to everyone. No matter where I add the yellow, if I add the yellow there, now in order to get round that yellow, I've got to add loads of cells to red. So it's just never, you can never be efficient like that. If we add the yellow there, let's just deal with that one. That's probably the most efficient place you could add the yellow, but I'm pretty sure we have to make sure we have a wing. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, it gets close actually. It gets close if you put the yellow on the boundary. 4, 5. Let me just double check that this is 10. Yeah, that's 10. There's no way of doing it. If you don't use a 3x3, you can't sandwich a region at all. Yeah, so I've spent 30 minutes talking about this. I'm so sorry, but I didn't understand it, so I had to figure it out. But I think I have now figured it out. There is no... you're all going to castigate me as well, aren't you? It's always one of the hard things when I don't understand something. There's always many of you out there that do, who will be very keen to tell me how slow my brain was. I'm sorry it's been so slow, but I do now, I think, have more feeling for this. You simply cannot create a Sudoku grid with, I'm going to say even 10 cuts of the border. I think is very difficult to achieve if you also have the condition that every border segment that you create is at least 2 cells large. And that is hard to, at least for me, to visualize, but I think it is true. And given that that's the case, that means that when we think about our factorization of 156 and how it's going to work in the context of this puzzle, we know that we must be heading up to a multiple. It's got to be a multiple of 13. Yes, in fact, we now know. We now know what it is, don't we? Because it's a multiple of 13. Don't pull out the cord that attaches this to this. Let me just double check it is still on. That's good. Yeah, so now, because we know the total along the border must be a multiple of 13, it can't be 39, because that would imply that we're only 4 regions in the border, which ordinarily could have worked, except that Zeta-Math has put 5 cells in the border, which must all belong to different regions. So we're not dealing with 4 cells, we must be dealing with 6 cells, which is the other multiple that we have available to us. No, we're not 6 cells, 6 regions. So we're dealing with 6 regions, each of size 26 in the perimeter. That's what I think we are doing. Now, that all said and done, what on earth do we do with that knowledge? Right. Okay, well, how about we do this? If we're dealing with 6 regions in the perimeter, each of which is summing individually to 26, we know that each circle in this perimeter must have a digit in it that's at least a 4. and not a 7. So it's 4 5s and 6s into the circles. And that's because if I'm going to make 3 digits, yes, yeah, this is right, I think. If I add 3 digits together in a Sudoku, 7, 8 and 9 only add to 24. We know that each segment is adding to at least, well, it's adding to 26 exactly. So it must be it must contain 4 digits at least, given that all the digits have to be different within the same segment, because within that segment they're all in the same region. Now, they can't have 7 cells in it, because if you had a 7-cell segment containing different digits, the triangular number for 7 is 28, and 28 is bigger than 26, so that doesn't work. So that's the perimeters cells. Oh, look, actually, I've just noticed now my givens are suddenly important. Those are not 4. This is a 5. I've got a digit. That's a 5 by Sudoku. Well, it's not really it is by Sudoku, but only after you've done half an hour of thinking. So that is a digit that's sort of available, but it's not a very easy digit. So that is very lovely. Now I've got 4 5 pair in this column. And now I'm wondering about an equation, because one thing we do know is that all of the perimeter I've just realised something. I've got 5 circles in the perimeter, but I've got 6 regions in the perimeter. So there is an unknown circle somewhere that we've not been given. I was about to say that I could add the circles up and get there's 28 cells along the blue line, so I was going to add the circles to get 28, but that won't work because there's another circle that is not here, that we don't know what that is. But the circles we have got add up to 14, add up to at least 23, and we're heading up towards 28, aren't we? Yeah, but the circle we've not been given, if we had been given it, it would have contained at least a 4, because you need 4 cells to add up to 26, or 4 digits to add up to 26. So hang on. So that means, so if I've got 9 here, 14 there, there's at least a 4 missing from somewhere. So that's 14, that's 18, and I'm heading up towards 28. So this could be, well, those could both be 5. But that can't be 6 ever. This cannot be 6, because if it was 6, 6 plus 5, which is the minimum, would be 11, 16, 25, plus the 4 at least that's missing. It might be more than 4 that's missing, but that's 29 cells, and there are not 29 cells on the blue line around the perimeter. So that is not a 6. It could, I think, be a 5, and that could be a 6 if that's a 4. Okay, well that's interesting. What on earth do we do now? I presume, I'm just wondering about this line, but this line terrifies me, to be honest. I've no idea how we're ever going to work out what that line adds up to. We can't use this line. This line is not important, at least not now. So we must have to sweat the outside line a lot harder, I think. So, how do we do that? These two add up to 9. So there must be line segments with 9 cells in that belong to these two circles. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Ah, no, that's not right. I was about to say that this cell can't belong to that. Actually, that might still be true. But I was just worried about the hidden circle, whether that could be a hidden line segment. But I think actually it's the same. It doesn't work. If this cell is not belonging to this circle, for whatever reason, either because it's part of the 5 or because it's part of a hidden region or a hidden circled region, that would mean that these two line segments had to fit in to just this part of the line. But we know there are 9 cells in the 4 and the 5, and I don't think that is 9 cells, it's only 8. So that means this cell must be the same region as the cell beneath it, which is a tiny little deduction, but I'm happy to take it. Now, can we go further than that? We can say that, so now this one, which is of length 5, can't reach there, so 1, 2, so these two have to be the same. Okay, well we are getting a tiny bit of progress therefore. Now there isn't enough space to fit in a 4-cell region that's not red and not yellow into this little line segment here. So these 3 cells are comprised of either red digits or yellow digits. So if this is a 4, you have to put a 9 on its line. No, well you do, but this is beautiful. Right, that 6 is absolutely beautiful. Well, actually that 6 combined with these 2 circles is beautiful. If this is a 4, the puzzle's broken, I think, because if that's a 4, that's a 5. And now think about how this line segment, the other 3 cells on it, they do have to have a 9 in them. They have to add up to 22. But if they have to add up to 22, they must either be a 5, an 8, and a 9. Well, they can't be that, because 5s are looking at every cell on this line string of line. Or they are 6, 7, 9. But that's the same problem with this 6. This 6 sees the whole length of that line. That cannot be a 4. That's got to be a 5, which means that's a 4. Now, what does that mean? Right. I tell you what that means. That means this circle here has to reach at least this square. And the reason is, if we say that this 4 doesn't ever get into row 1, so it's just maybe those 4 cells, for example, how is it comprised? Well, these 3 squares have to add to 22. Therefore, they're either 5, 8, 9 or 6, 7, 9. And the 5 and the 6 would rule both of those out. So this has to get out of column 9, and therefore it must come at least to this square. So these 3 squares are all the same, and therefore that square, which is penned in, is now a purple. Good grief. Now this, which is of length 4 at least, must come to at least this square, mustn't it? So all of those 3 have to be the same. There's only 3 line segments here, so these squares are purples and yellows. These squares are yellows and reds. We still haven't discovered the missing circle. Sorry, let me just think about this now. Also, I've got to remember that I was just wondering, you know, if this goes all the way up here, you can get a very precise count on this column. You could get that digit. Yeah, you could, because if those 5 cells are all yellow, we know that they add up to 26. Now 26 plus 6 plus 4 plus 2 is 38, and this would be a 7, and that looks possible, because the secret makes the column add up to 45. So I can't rule that out. If that was yellow, that would become purple, and that would become green. Is that green? That looks tricky. If that's green, then we know that green is a 5 here, and these 6 cells would add up to 27, because these would add up to 26 plus 1 is 27 plus 2 is 29. That means these two have to be a 7-9 pair, and they have to be purple, which doesn't work, because if they are both, well, if those are both green, that means green can't take this square as well, because it can only be a 5. It's going to be a 5 by the time it takes those 2 squares. This now has to be purple, which completes purple, which means that once we put the 7, 9 here, in order to make purple add up, we have to put 6 there, which clashes down there. So that's, well, so this is not green. So this is something else. We don't know what. But does that affect that digit or not? Or is it the same logic? Actually, it might be the same logic. If that's green, we've got the same, yes, we've got the same sum. It's the same, yes, it's the same. Exactly the same logic. We've proved this isn't green, but we've also actually proved this isn't green either. Because if that's green, we have exactly the same mathematics. We've got 26, 27, 2. That's got to be 7, 9. And that's got to be still a 6 again. So that's not green, which means it's the same colour as the corner. That is grey. So now, this is getting squeezed in. Now, if this is right, and if this is grey, I don't know whether it belongs to this or not, but we do know that every line segment around the perimeter is at least of size 4. So 1, 2, it's got to take these 2 as well. Those have got to be grey. Okay. Slowly and steadily we are colouring this. So if that's 5 now, it would complete row 1. So these would be the same maths again. These would have to be a 7, 9 pair, wouldn't they? Oh, no, that doesn't work. No, that doesn't work. Sorry, because the 4 needs to have a 5 or a 6 in it. And the 4's 5 and 6 clearly cannot be in column 9, so it needs to be up here somewhere. But if that can only be 7 or 9, that doesn't, yeah, this doesn't work. If these are green, this is 26, 27, 28, 29. That means those 2 squares add up to 16, which means they're a 7, 9 pair, which means that this is a 7 or a 9, and it doesn't matter. We can't make the total work, because we either need the 4 to be accompanied with 5, 8, 9, and there's nowhere for the 5, or we need it to be accompanied with 6, 7, 9, and there's nowhere for the 6. So those 2 are not both, well, if those 2 are both not green, then that's a 4. Which means there's a 9 in, goodness knows how, one of those cells is a 9, because the 4 needs a 9 with it. That means this isn't a 9, which means there's a 9 in one of those 2 cells in column thingy thing, column 9. So So if that's yellow, that forces that to be 9. And that looks like it's going to make this column add up to a lot. If that's 26, 36, yeah, that's beautiful. Right, that's not yellow. Because if that's yellow, these 5 cells add up to 26. We know the 4 needs a 9 with it, and the 4's 9 must now be here. And the column adds up to too much. 26, 36, 38, plus 9 is 57, which doesn't work. So that is not yellow, which means it's purple. And that finishes purple. It finishes purple. So that's got to be green. And that finishes green, which makes this grey. Good grief. And now those have got to be yellow, which means yellow needs 1 more, which means that's yellow. You can't fit an extra region in here, so that's a red. Red is finished. Yellow in the corner, that cell's got to be yellow because it can't be another colour, it can't connect to anything. Good grief, we're actually getting this done. Now, this square is now a new colour. Do I know it's that colour? No, not necessarily, I think. It could be a 4-cell region like that, connected with the 3. I mean, I know that these... Yeah, I mean, I know that this must be a 4-cell region at least, so it must take those 4 cells, which means it definitely includes the 3. But what we don't know... oh, I don't want to put orange next to red, really. How shall I do this? Maybe I'll make this purple, because I don't think this is going to connect with this. Now that means these 2 squares, well, that could be purple, but can this be also grey? If this is grey, grey would be too big, wouldn't it? 1, 2, 3, 4, 5. Oh no, it wouldn't, because I keep wanting to put the corners into the blue line calculation, but the corners are just not in the blue line calculation. So these 2 squares are purple-grey in some order. That's no longer a 9, because we know that the 9 belongs to the 4 clue. This square is now a 5 or a 6, because we know that this 4 clue needs a 5 or a 6. Ah, so that means I should be able to work out the value of this cell. Well, within 2. It's got to... Yeah, but just by mathematics on this column, that must work. So if this is 5, these cells add up to 21, which means these cells add up to 24, but this cell isn't on the line, so this 24, these would add up to 18, which makes this square have to equal 8, I want to say. I've lost my train of thought now, though. This is 5, this is 8, 9. If this is 5, these add up to 20. Hang on, if this is 5, these add up to 21. That's 23. These add up to 22, but this isn't on the line. So these add up to 16. And that gets me a 10 there. This is... oh, I've messed this up somehow. I'm not understanding how it works. Why can't I do this? This is just maths, isn't it, on this column? What is it I'm not doing? Is it because I don't think about the corners properly? The line segments add up to 26. So these... oh yeah, maybe that's a way to do it. Yeah, so these 9 cells add up to 52. 52 plus 8 is 60. Oh, so that can never be 5 because that would be 10. Yeah, okay, that at least I've got 10 twice now by doing this. I think this is the way to think about it. Maybe I'm overcomplicating this, but those cells and these cells, there's 9 cells there. We know that they add up to 2 lots of 26, which is 52. 52 plus 8 is 60. Now, but I know this column overall adds up to 45, so these two have to add up to 15. So if that's 5, that needs to be 10. If that's 6, that has to be 9. I think that's a 9. That's a 6, which means those have got to be equal to a 7-9 pair to make this add up. I'm just going to double check the maths here, but no, 4, 10, that's 16, that's 26. So these squares are now known to be 1, 3, and 8. And hopefully if we add those digits up, we'll get 26, 14. Yes, we do. Good. Now I can get this digit just by, using the power of maths again, hopefully a little bit more cleverly than I did last time. So they're 26. Ooh, that's got to be a 1, I think. I'm just going to double check that. 26 plus 15 is 41. Those have to add up to 4, so that's got to be a 1. Ah, and that's very beautiful, because now how can this not be purple? If that's not purple, these 3 squares have to add up to 25, and that won't work. 7, 8, 9 only add up to 24. So that is purple, definitely. Do I know whether this one is purple or not? The answer is probably, but I don't know how to do it. Well, I don't know. That's I suppose the technical way of describing it. Somebody knows, almost certainly, but it's not me. Having said that, I very nearly coloured the outside of this grid, which I do feel relatively pleased about. Those squares have got to be 2, 4, 7, and 8 in that row. Ah, now I've got a 6 here. So this can't be 6, 7, 9. That has got to be 5, 8, 9. That means these 2 squares have got to be a 3, no, not 3, 4 pair. I've already got 3 here. 3, 7 pair, maybe? So this is a 3, 7 pair. That's 10. Ah, that's it. Beautiful. So now, this can't be a 4-cell region, because if it was, this domino would add up to 16 and would need to be 7, 9. That would repeat 7 in the grey. So that must be grey. And if that's grey, now we know what this is, which is 5. 1, 2, 3, 4, 5. Yes. So that's 5. There was a hidden 5 region after all this. I'm just going to double check this. I've got 9. Oh, I've got 18 there, 23, and 5 is 28, and that is how many cells I've got in blue. Good grief. Good grief. So now 7 in column 1 must be in one of those cells, which means we can work out the value of the other domino down here, can't we? Because we've got, at the moment we've got 6, which means these 3 squares add up to 20, one of which is a 7. So 2 of the other cells add up to 13, and they can't be 6, 7, and 5, 8, so they've got to be 4, 9. So this is 4, 7, 9, which means these squares are 2, 6, and 8. And I'll tell you what's amazing about what ZetaMath has done here, and that is that this puzzle is it's entirely self-contained. Figuring out this ring that we've done, we didn't even need to use the central 7x7 of the grid at all. I suppose we needed the 4, but that's it. It's like a puzzle that exists outside of Sudoku world. Fascinating. It really is. It's Fistomaphelian is what it is. This logic, this early logic, reminds me of a Fistomaphel puzzle. It reminds me a bit of that one I streamed, actually, that had the funny funny region ideas around the edges. Now, what do we do with what we've just discovered, though? I've got a horrible feeling about this. I've got a horrible feeling I need to use this line now, which is not an appetizing prospect for me, at least. That's not a 5. Let's see if Sudoku can help us. I've had an hour. I've got about 4 digits, 5 digits in the grid. No, 6 digits in the grid. I'm a lie. Oh, 8 digits. I think I've got 8 digits actually. Well, we're practically done. That's not a 4. No, the problem is that this is not going to do enough damage, is it? We are going to have to think about something else. So, how does this line work in the context of what we've already discovered? We have discovered that we've put 26s into all of these regions. So we can't put more than 19. Yeah, so what I'm thinking is this green region definitely has to hit this line in at least one position. I mean, it might come out and do something strange like this. But this digit then definitely hits the line. Now, the same with grey. Grey must hit this line. The same with purple. Purple must hit this line. It's not the same with red. Red could hit the line, but doesn't need to. Oh, actually, this purple also... Yeah, that purple is also sort of penned in by the line. I'm just wondering, is it possible then that the number on this line is 19? I.e., this line is going to get divided up into 19 regions, entirely therefore completing the regions that we know must touch this line. So 1, 2, 3. So this needs 4 more cells on it. This needs 5 more cells on it. 4, 2, 3, 4, 5. The grey needs 3 more cells to add up. Oh no, that's not right. The grey... No, am I talking nonsense? I am talking nonsense, aren't I? Because it's true that the green needs 19 more, because the green has 26 only in it. But it's not true that the purple needs only 19 more, because that too is not on it. So the purple only needs 17 more on the line. So that means the green can't have all its digits on the line. Because if the green did have all its digits on the line, we know that the green would add up to 19, which the purple could never add up to, because the purple's already got 2 hidden in the corner. So some digits from green must escape. So 19 is not the number on the line. I think that's all I've proved. 19 is not the number on the line. Ah, but grey doesn't have many digits that it can put on the line at all. 4s, 5s and 9s. 2, 6... Good grief, right. So the number's 14, isn't it? The number's 14. That's so clever, Zatamath. That is so clever. Good grief. How do you set stuff like this? It is absolutely mind-bending. The number's 14, I think, because we know that each region that is contributing to this internal line needs to contribute the same total to this internal line, because it's one of these region sum lines. Now that's not that easy actually, because purple only has the digits 2, 6 and 8 to give to the line, and grey only has the digits 4, 5 and 9 to give to the line. Now, so for example, let's imagine that grey contributed a 4 to the line there, and that was the only digit it contributed. Well, we know purple therefore must contribute digits summing to 4 or a 4 itself to the line, but purple's already used its 4, so it can't contribute 4 to the line, or 1 and 3, it won't work. So we have to think about common possibilities between the digits that are capable of being contributed to the line by things like the grey and the purple region. Now, because the grey region has only got 4s, 5s and 9s to give, and the purple region has only got even digits to give, given that we can't just be 4 here, we know we're heading to an even total, which means we need to use both odd digits to get to an even number in here. But 5, 9 and 4 does not add up to the same total as 2, 6 and 8. So we know we have to find a lower common number, and the only way I can see of doing it is 5, 9 up here and 6, 8 down here somewhere. So I think it's 14. So this one must contribute 14, this must contribute 14, this must contribute 14, 1, 2, and therefore it's only got one digit. The 4 needs to sit somewhere around there, I think, maybe there. I'm not sure, that one might be possible as well, although that's ruled out by this. So the 4 is going to get very constrained by the grey. The purple must contribute 14. And we don't know about the red. That could contribute 14 if it starts snaffling cells up here. Oh, this is so ridiculous. Right. But what is the nature of that cell? That's the question I want to ask. What is its nature? In particular, is its nature unpurpleable? Is it not of purple extraction? Now, if it's not of purple extraction, let's think about how it could possibly move on this line, given that it needs to add up to 14. Well, what it cannot do is be a 3-cell segment adding up to 14, because that gives no escape for purple. So its only option would be to be a 2-cell segment adding up to 14, but 6, 8 and 5, 9 are not possible. So that is not possible. So the nature of this cell here is therefore purple. Now purple must be at least 2 cells because we're adding up to 14. Although actually no, it's not, it's 3 cells because we've already used 6 and 9 in purple, so it's got to be 3 cells. I'm just questioning whether it could be 4. No, 4 cells, because this is 5 cells already. Oh no, hang on, let's do the maths. 26. Hang on, I might have got the maths wrong here. 26, 28, 17. 17 is not 14, yes, so there's a missing 3 off the line. So this purple line must be made up of the digits that are 1, 5 and 8, which do add to 14, and there is a 3 off the line. So there's a 3 here, here or here in purple. This is just so clever, I cannot tell you. So now does that mean this is green, or could this be another region coming onto this line? That's the question. So green's already used a lot of its high digits up. So green's got 1s, 2s, 3s, 6s and 7s to give, and it needs some combination of those to add up to 14. So there's only one way of doing that, I think. Must be 6, 7 and 1. So green is contributing 3 digits to the line. This is ridiculous as well. This is ridiculous as well, I think. Certainly in some regards it's ridiculous, because let's imagine that this is now a rogue digit. Alexa again, what are you doing? Alexa, I didn't summon you. So green is contributing 6, 7 and 1 to this line, and wherever those green cells go, they're definitely in row 2. I can't get a green 6, 7 or 1 down here. So there is some 6, 7, 1 combination over here, or possibly in this cell as well. But you can see that's very interesting. It means this is a 9, and it means 6 is green in the row. So that means if there is an interloping region here, it can't be a 2-cell interloping region, because this would have to be either 9, 5, there's a 9 here, or 8, 6, which there's a 6 in the green. So it has to be a 3-cell interloping region, which means that these cells would become 1, 6, 7. So this would be 28. That would be 37, and these two squares would have to add up to 8, which they can't. So I don't think that's possible. Let's just double check the maths on that, because that is fairly complex. If there's an interloper here that's not green, I'm happy it can't be a 2-cell region. So it has to be a 4-cell region. No, 4-cell region completely cuts off green. So it would have to be a 3-cell region. We'd have 1, 6 and 7 placed into these cells, which would be green. This would be 14. This would be 14, so these sum to 28. That's now a 9, so that's 37. These two have to sum up to 8 to make 45. I cannot see how that works. So this is wrong, and that is the sort of wrong I like, because now I think we have proved that this is not an interloper. That is green. Green needs to contribute exactly 3 cells. So this is a 1, 6, 7 triple. That square becomes a 9. That square's not a 6 anymore. That square's not a 1 anymore. This is fabulous, isn't it? It's fabulous. Now it's going to get more difficult, I suspect. Because what's the nature of this digit? Oh, actually, hang on a minute. I might have broken the puzzle, I fear. Oh, Simon. I can't. Oh, no, maybe I haven't. Okay. What I was suddenly realising is that the grey digits I've got to contribute to this blue line are 5 and 9. And I can't do that in that square, because although I could make this a 5 and this a 9, that would be a 2-cell region, which would need to add up to 14, which it can't do because the 6s and 9s are not available. This obviously can't be 5, 9. This can't be 5, 9 because there's a 9 here. This can't be 5, 9, I've just proved. So the 5, 9 is either there with these 3 digits adding up to 14, which we've already shown can't work because we needed those two to add up to 8, which they don't. So that implies that is a 5, 9 pair, which we know the order of, with these 4 cells adding up. Oh, good grief. Right, I want to check this, because if those... No, I can't see that. I use red because red's down there and it probably doesn't connect. But this, to be a 4-cell region adding up to 14, it hasn't got a 1 in it, look. So that's got to be 2, 3, 4, 5, and I have a horrible feeling that I've broken the puzzle. Although I don't actually see, it doesn't seem to break immediately at least. So this has to be 5, 9 now, which means we know the order. So that's 5, that's 9. Which means that's not 5. What digit is it we've still got to put in grey then? 4. Ugh! No, that's okay. That's just okay. Where does the 4 go? Oh no, hang on. No, I can't put the 4 on the line. Yeah, where does the 4 go in grey? The answer is not there, because it would be on the line, and this line would not add up to 14 then. Not here, because there's a 4 there, so it's got to go there. So that's 4, and that's grey. Oh, now this red region's getting very tricky. That's got to be red for the red to get out, which means that's red, because the grey is now finished as a region. In fact, that means I should ring it, doesn't it? There we go. We're going to award it its own special status of completeness. And say FRAK in joyous exultation. So, now what does that mean? Ah, that means that's not a 4. Now I'm wondering about purple. Is that the thing we need to worry about now? I know that purple is contributing 6 and 8 to the line. I also know, yes, I do know, this is great. You can't put 6 or 8 in there because that would imply the line segment is 6 or 8 long, which it can't be because the purple is only contributing 2 cells to this line. So I think that has to be the 6 and the 8. I don't see another way of doing that. So this is a different, right, now you can't, yeah, this has to not be purple, has to add up to 14 and has to include a digit here that doesn't divide this line segment into 2 segments, because you couldn't make, you know, that if that was a segment adding up to 14, you'd have a big problem with this cell, which would have to be a 14 on its own. So this surely is a 3 line segment, with this being a 3. And these 3 are all the same, which could probably be red, actually. Let me think about that in a second. Let me just label that up. I'm going to label it green, but I think it could be red, because 3 hasn't appeared in red. And those 2 would add up to 11, which doesn't work. Wow, no, that's wrong. Okay, green is not red. This is another thing I'm going to reveal to you. You may have thought you knew that already. Well, you didn't in the context of FRAK, because, well, you might have done. But anyway, these definitely cannot join. Green cannot join red, because these would have to add up to 11, and 2, 9, 3, 8, 4, 7, and 5, 6 are all unavailable. They'd all lead to a repeated digit in the region. So green is a new region. Now, what digit have we not put 2? We've not put 2 in. There must be a 2 in one of those cells to complete purple. 6, 7. And that will complete purple because we've got 8 digits in purple. So there's a 2 in one of those, which means that's not a 2. 3 here means that the 3, 7 at the top is resolved. Which means, that square seems to have to be a 5. Why is that? How did that not be? How is that not a 2? Oh, from the 2 I've just identified there. Yeah, good grief. Okay, that is a 5 then. So that's not 5. Those aren't 5. Those are not 3 either. So this is a 2, 4 pair, and this is a 3. My phone is buzzing. Oh, hang on. I just need to. Oh, I've had some bad news there. Anyway, I can't. Let's carry on. Now, 5 here goes to 8 here. That must be a 1, and that must be a 5. And that must be a 7 by Sudoku. Now, what's the digit we've not put in purple? It's 3. But, rather annoyingly, there seem to be a few possibilities for where that 3 might go. Okay. Now where do we look? Now where do we look? We shall look at... I sort of want to draw this boundary in a little bit. This 8 is giving me a 2 over there. So that's 2, that's 4. This is not 2, this is a 6, 8 pair. This is a 6, 8 pair. 3, 4 and 5. No, that doesn't work down at the bottom. This column's got a line in it, so we need 2s, 3s, 4s and 7s into this little thing. Right, that's useful. So this is a 2. Because the nature of one of these lines is that they're equal sums. So we need one of the digits on this line to be the sum of the other 2 digits. And the only way I think that can work is 3 plus 4 equals 7. So you can't put a 2 on this line, so this is a 2. 3, 4, and 7 must be at one end. Because if you put 7 in the middle, it won't work. Because you can't connect these to each other and say it's all in the same segment. So 7 is not the middle digit. Well, 7 is not the middle digit. And I don't know that this can be the 3 now. No, it can't, because if this is... Oh, that's not 4 either, I just noticed. But if this was 3... Well, when I say it can't be the 3, it can't be the purple 3. Because if that was the purple 3, then the 4 would need to be in the same region as the purple to make the maths of this line work, and it can't be because we've already got a 4 in purple. So 3 in purple is now in one of those 2 cells. And green needs a 3, and green needs a 2 and a 3. Where does green get a 2 from? So oh, this is really clever. Right, so that's the purple 3. Because green needs a 2 and a 3 and can't get a 2 in row 3, green must get a 2 in row 4, so somewhere over here. But the only way of connecting to the 2 that must exist in row 4 is via a 3, a green 3, in row 3. So if we tried to make this the green 3, this would be a 2, and there would be nowhere to put a 3 in purple. So the green 3 is in one of those 2 cells, which means that's not a purple 3. So that's a purple 3, I think. That's gorgeous. And now I've finished purple, so I'm going to definitely hive it off. One of these 2 squares has to be a 2 now, because whichever one of these is 3 is going to have a 2 beneath. Oh, it can't be there. If that's 3 and that's 2 completing green, what's this square? And the answer is not a lot. That won't work. So the 3 must go here. This is penning in the red. So this is green completed. Green is finished, so we can ring it. Now red is all... Red's struggling now. Red's got to come out along this blue line. And... can't come there. Look, if that was red, we'd have 2 4s in red. So red is not coming that way. Oh, I'll tell you what else red can't do, I don't think, if my understanding of the rules is correct. I don't think that can be red. Because if that's red, this line has exited red and come back into red, which would mean this line segment needs to add up to the same as those 4 digits add up to, and that won't work for many reasons, but this would have to be an enormous digit, and that won't work. So I think that might be the final red piece of the jigsaw. So we've got a comma in red. Wow. This 4, no, that doesn't do anything. I was about to say it resolves this square. No, I know it doesn't. Well, I do now. Oh, this is a new region. Yeah, that's a new region. That's got to come out. I feel like there's another colour I could use here that would be orange. Oh, yeah, I could use orange up there. I'm going to use orange. That feels a little bit less bleak. Ah. How could that be 2? Purple 2? If it's a purple 2, it's the only purple 2 on this line. And that would say that this needed to add up to the same as that. That can't work. So that's 2. Sorry, that was really simple. I just didn't spot it. So that's a string of digits now. So that's finished purple. So what does that mean? We've got an awful lot of lineage in this bottom part of the grid, and quite a lot of high digits on this line segment here. This line here is 1, 6, 7, 8 or 9. Unfortunately, well, we know those are not 9s. We know that that's not 1 or 7. Oh, so this row needs 6, 8 and 9 to finish it off. This needs something. No, that's no use. So the minimum value of this line now would be to put 1 on it along with 6, 7 and 8. 6, 7 and 8 is 21, so 22 is the minimum value of this line. So this cell, which is a 4, in order to get to 22, needs 3 more. Oh, this is beautiful. Good grief. Right. This is important because the sum of red on the line, on this line here, is at least 22. This cell needs to get to a 22 count. Well, it can't go double 9 on its line in the same region, so it must be 3 more cells at least on the line, which takes it to here. But now this cell must be the same as this, because otherwise we need 1 cell in the grid that's a 22 or more. So this is like a T-pentomino of the same. That's all the same. Now that looks quite tempting to join up with this, doesn't it? How do we do this then? 4 here, 5 here. That would create a 9-cell region, which would look rather splendid. No. Ah, no, that's beautiful. Good grief, it's still giving this puzzle. It's still giving clevernesses, because how could this be orange? The answer is it can't be. Let me explain why. I'll make it all dark coloured. So, if this was a 9-cell region, we need to think about this region. We know that the green region is not the same as the red region, so this green region needs to grow. But this little 1-cell line here stops it growing, I think, because it's not possible that both sides of this line are in the same region. They must be in different regions. So if green grows to here, this cell is isolated and can't join another region. And if green takes this cell, this is not green, and green can't get out. That's just so clever. So now I can draw this line segment in, because orange is not black. Another statement of the obvious, it would seem, but not in the context of the FRAK puzzle. So now I feel like I've got too many regions in the puzzle, actually. How many actual regions have we got? 1, 2, 3, 4, 5, 6, 7. This green is not red, so that's 8. Oh no, hang on, rather than doing it like that, I know that the 4 is not the same as the orange, so that's the 9 regions. That is the 9 regions. So that means that green has to join up. Yeah, so that means green has to join up to a region that has already got a highlighted cell in it. Well, it can't join orange, because there's no way, it would be too big. It just would be, it would be too big. We know it's not part of red. It can't join yellow, it would be too big. So it must join black. So this is, which connects to green, that's annoying. I might have to go, I know people don't like me using black, but I might have to just for a moment or two until we can secure. I could make this yellow. I can make this yellow. There we go. Because I don't think this yellow is going to touch this. It might do, and that would be annoying, but at the moment it's not. Now this cell's isolated, so that must be yellow. And that completes yellow. That completes yellow. So that's it. Right, so yellow is now done. even more beautiful, what are those two cells? They add up to 11, and now I've managed to get a 4 into the yellow region and a 2 here. So the only option for this is 5 and 6, and there's a 5 up there. So this is 5, this is 6. Those are not 6s anymore. That's not 5 anymore. 5 in the top row gets placed by our old friend Sudoku. Fancy you making an appearance in this puzzle. Outrageous. That's not a 2. So 1s, 7s, 8s and 9s into these cells. This is where it's going to get very tricky, I think, because we're going to have to keep a careful track of Sudoku in the regions, which is never my favourite thing to do. So this one presumably is red, is it? What else could this be? It can't be yellow, because yellow's going to then cut off red. If it's orange, oh, maybe it can be orange. Although that doesn't leave red many places to get out, does it? Yeah, that's interesting. I don't think that's going to work. So if orange takes this cell rather than red, red has to take this cell. Now red can't come to this square because that's a 2 and we've already got 2 in red. So red has to go to that square. 1, 3, 6, 9. Where's red getting a 3 from? Yeah, red can't get a 3 from anywhere. It doesn't work. Because red, you might think red can get a 3 from one of these two squares, but remember it can't, because the 3 is necessarily part of the same region on this line as the 4, and red already has a 4. So it can't get the 3 from here. There's a 3 here. There's nowhere for it to get a 3 from. So this is wrong. There's probably a simpler way of proving that, but that's now red. Now, what can it be then? It's got to not be, it's got to be either 1, 3, 6 or 9, I think. Just looking at what's left to place in red. It's not 3 or 6 because there's a 3, 6 there. So it's 1 or 9. Which means that square's 1 or 9. Which gives me a quintuple in that column, I think, on 1, does it? 1, 6, 7, 8 and 9? I think so. That seems to be right. So that square is not able to be 7 or 8 anymore, so it's 2 or 4. Is that the miss? Yeah, okay. So that makes this a 2 or a 4, but there's a 4 here. So that's a 2, that's a 4. That's the world's most disappointing 2, I think we can describe it as. Aha! Right, how could that be 9? The answer is it can't be 9, because if it's 9, that is also 9, because these have the same sum in their regions, and now you can't put a 9 in green at the top, so they must both be 1. So that's not 1, and these aren't 1s, and that's not 1, and that's not 1. Now, right, and now I know the sum of this, don't I? I think, because all of those 4 digits are the only ones that aren't on this line. So this has got to be from 7, 8 and 9. Oh, and that gets me a 6 at the top. So we're starting to make progress here. We've got 24, 30 on the line here. So these 4 cells have to add to 30. There's only one way of doing that. We can't use the 1 anymore. It's got to be 6, 7, 8 and 9. So that's got to be a 1, which means that's a 1 in that column. 7, 8, 9, 6. In this quadruple, this 6, 7, 8, 9 quadruple, the 6 and the 7 are in this string, so that's not a 7. The other way of seeing that is that that digit and that digit have to be the same. Still doesn't seem to actually be resolved, though, rather worryingly. I don't know. I've still not looked at this line. Okay. That's good and all, but how do we finish this puzzle off? Is that the state? Oh, that's a 3 here. That's got to be an 8. So that's a 3. Oh, that's a 7. 3, 4 pair here. The other thing I've got to be a bit careful of is this 3, 4 has to join a region that doesn't have either of those digits. And bear in mind, that means it has to be orange. No, no, no. Does that work if that's yellow? What I'm thinking is, we know this line is divided up now. Well, we can do that. That line segment is forced because the 7 must be different from the 3 and the 4. But yellow already has a 3 in it, and red already has a 4 in it, and the only other region available is orange, so I think they have to be orange. Now this now definitely can't be red, because red would have to plough a mighty furrow through the orange, so that must be yellow. So 1, 2, 3, 4, 5, 6, 7, 8. The minimum way we could connect orange to orange here is now with 8 cells. So there's no way this cell can now be orange anymore. 2, 3, 4, 5. And it can't be yellow because it's too far away from yellow. So that square's now red. Now what do we need in red? We need 3, 6, and 9. Hang on a minute. We need 1, 2, 3, 6 or 9, I think. I think that's a 9. I've a bad feeling about this. I don't like this 3, 4 for some reason. That's a 4, 7 now. Which, actually, that's a 4, 7. And that cannot join. 4 and 7 have both appeared in red. And I don't think this can be orange because there's no way of connecting that orange, and that domino of orange together in 9 cells. Let's try and do it. No, you can see just linking these two creates 2 4-cell regions. So I need to have 1 cell to connect this to this, and you can't do it. So that square, I think, has to be yellow. And if that's yellow, that means that's yellow. Or does it? Yes, it does, because I've got to connect the yellows up. So yellow is now done, and that square should be a 4, which means that square is a 7. Now if yellow's done, that's forcing red out, isn't it, up to this cell, which we know is a 3 or a 6, because those are the 2 digits we've got left to place in red. I'm going to end up with orange touching orange here somehow, which I don't like to do, but I could change orange to grey. I think that's what we should do, so that we don't run into colourblind issues. Now, yellow is done, so let's fill that in. So red has got 1 more cell, so either this or this is red, which implies both of those are grey. So grey is taking 2 cells at least on this line. It could take, oh no it can't, right, here you go. So if grey takes a 3rd cell on this line, this would have to be a 6, and this would have to be 1, 2 and 3 to make it add up. That's the minimum we could make 3 digits add up to, and the 3 here prevents that. So this cannot be grey and must be red, which means it's a 3 or a 6, which means this square is a 4, this square is a 3, 9 here, this square is grey. I think that's the colouring done. Let's just take a stare. Do we have 9 cell regions? It looks like we do. Now, can we get... Now, that square's got to be 8. That's got to be 6. That's got to be 9. That's got to be 4. This square's got to be 7. Those two squares have got to be 5 and 7. And there's a 5 here. So 5 and 7. This square's got to be 2 to make the line work, because 3 plus 6 is 9, so that's got to be 9. That's not 7 anymore by Sudoku. So this should be 6 or 8, which somehow is not resolved. Probably is, I'm just not seeing how. I've got an 8-9 pair in that column, so that's a 7. I've got a 2-8 here, a 2 here, that's good, keep going, 2-8. The 3 here gives me the 3 and the 6. The 7 here, there's loads of Sudoku I could have been doing, never mind, you know me. 9 here means that's an 8, that's a 6, so that should be a 7, that should be an 8. This has got a 9 in its region, so 6, 9, 6, 8, 9, 8, 8, 9, 1. I think I might have solved this puzzle. Only took me, that's a long time, that's 100 minutes. That is a long time. I'm so sorry if you're bored of listening to me. Let me think. Yay, looks good to me. I can't believe it. I can't believe it. That is just mad, isn't it? Absolutely mad. That's very difficult indeed, and very, very clever. I mean, well, that's not doing it justice, to be honest, to describe it as very, very clever. It's almost inhumanly clever. The idea about the equal sum lines around the edge, and the fact that that was actually resolvable ab initio just by putting a 4 in the middle of the grid, and you could actually resolve the structure of the lines because of these corner selections. That's really amazing. It's really amazing. But I think the do I even prefer this line? This line is magical. It is absolutely magical, because the consequence of the fact that you have different digits used in the perimeter, and that means you've got to put different digits onto the line in such a way that you can make it work, is so beautiful. And then that line also resolves itself. I mean, imagine trying to construct this again. It's just crazy. It's FRAK worthy, Zeta Math. FRAK worthy. Really amazing puzzle. I hope some of you managed to finish it. I'll be very interested to read the comments. I'm so sorry I've taken a long time to do it. I wasn't trying to take a long time. Hopefully you appreciate that. I'm sure there were any number of things I missed or could have seen more quickly. But we do these live, and that means that you get to see all of our brain-melting, appalling solving, as well as the good things that we occasionally do. But yeah, thanks for joining me. I will stop now before we have a power cut, and we'll be back later with another edition of Cracking the Cryptic.